Welcome. Let's talk about elimination reactions. So we've talked about substitutions, we've talked about addition reactions. The last one we're going to talk about is eliminations. Um, Again, similar but different from what we've talked about before. So let's jump right into it. All right. So an elimination reaction is going to be pretty similar to um, the substitution reactions that we've seen before, in that we're going to be breaking a sigma bond, right? So remember that eliminations we break two sigma bonds and make a pi bond. Oops. Right, so the reactions that we've seen before that have broken sigma bonds have been things like SN1 and SN2 reactions, and an elimination reaction is going to look more or less the same. So if we have, I'm just going to start with tert butyl bromide here. This can undergo an elimination reaction. We'll just heat this up in water or something, H2O and heat. This can undergo elimination reaction and make a pi bond. And so what we've done is we've broken, obviously, the carbon-bromine bond plus HBr. Right? We break carbon-bromine and a carbon-hydrogen bond, right? There's a carbon-hydrogen bond down here that's no longer present. And we make a carbon-carbon pi bond. Okay. So we end up making HBr, we make the pi bond here. We're going to lose this. So if we just think about kind of how would this reaction go, it would make sense. Well, hopefully at this point you're trained, you see the first thing we see is that we have a leaving group, right? So one of the sigma bonds that we're going to, one of the sigma bonds that we're going to break is going to be from that leaving group is one of the sigma bonds broken. And so it stands to reason that our reaction is going to be happening at this carbon, right, where the leaving group is attached. And so we look at this, we say, okay, this is a tertiary carbon. This is probably, if we use the same rules that we used in SN2 and SN1, what's going to happen is our leaving group is going to leave, and we're going to make a carbocation. Right? So we make a tertiary carbocation here. Now, as soon as we make a carbocation, we think about what are the things that this can do. We have to worry about rearrangement. Is a tertiary carbocation going to rearrange? Rearrange? The answer is no. We get no rearrangement because it's a tertiary carbocation. So now the question is, what else can happen, right? We have Br minus, we have H2O in our reaction. So we could have water come in and add to that carbocation. That would be an SN1 reaction. Right? The other option is we can remove a hydrogen from the neighboring position. Right? So the leaving group is one of the sigma bonds broken. The other sigma bond broken is from a neighboring carbon losing a hydrogen. And this is just a Bronsted-Lowry acid-base reaction. Right? So we have our acid, right? Our tertiary cation is going to be our acid. Positive charge usually implies acid. Our base, in this case, we have Br minus or we have H2O. H2O is technically a stronger base than Br minus. Br minus is a more stable base than water. And so when we draw this out, we would have H2O come in, take this hydrogen, and then that means that if we were just drawing the conjugate base, we would draw a negative charge in this carbon, but of course there's a resonance structure where that negative charge shares with a positive charge, and so we're just going to do this all in one go, and we're going to make the pi bond. So this is very much like an SN1 reaction in that there's two steps, right? First step, the leaving group leaves, makes a carbocation. Second step, in the SN1 reaction, we would have something come in and attack that carbocation. In this case, we remove a hydrogen from the neighboring position. This is called an E1 mechanism. The E stands for elimination. But E1 mechanisms always go through carbocations, right? So just like the SN1 mechanism, we always get a carbocation when we do an E1 mechanism. Okay? Now, so the difference between SN1 and E1, SN1 versus E1, right? Both prefer leaving groups attached to secondary or tertiary positions. Right, and the reason for that, the reason that secondary tertiary positions are favored is due to carbocation stability, right? If you're going to have your leaving group leave and make a carbocation, it needs to be a stable carbocation. So it needs to be a secondary or tertiary leaving group. Which one happens, right? Do you get SN1 or E1, right? Neither require a good base. Right? So we don't have to have a good base to remove that hydrogen to make the pi bond. We don't have to have a good nucleophile to react with the carbocation in order to have the SN1 reaction occur. And the reason that they don't require a good base is carbocations are very reactive. Right? Carbocations are not very stable, and so we don't need to have a good nucleophile or a good base to react with them because pretty much anything will react with them. Right? Generally, E1 reactions occur with heat, right? Whereas SN1 reactions tend not to occur with heat. But for the most part, SN1 and E1 are kind of hard to predict which one is going to go which way. I know that's kind of like the worst possible news that you can get is that it's hard to predict which way they can go. The key thing to look for in general is if you have heat, you're usually going to favor elimination, right? If you don't, if you're just running the reaction at room temperature or whatever, an SN1 is probably the more likely outcome, right? But if you have a secondary or tertiary leaving group and a poor nucleophile or a poor base, right? These two things here imply SN1 or E1, and then you would look at is there heat or not to determine what goes on, right? There are examples, so sometimes you can get things like if you have a situation where you have, let's make a benzene ring here that has a, oh, I don't want, yeah, we'll put another benzene ring over here, right? So in this case, right, if we, whatever, we'll just use methanol, right? So we have a leaving group, secondary position, it's got resonance stabilization. So this would be a stable cation. We have a poor nucleophile, a poor base in methanol, right? Neutral oxygen is a poor base, it's a poor nucleophile. And so this would be an SN1 or E1 process. Right? When we draw this out, in this case, when we make the carbocation, our chlorine leaves, we get this carbocation. Now, we cannot do an E1 elimination. E1 is not possible because there are no hydrogens at neighboring carbons. Right? So the second step of the E1 mechanism is to remove a hydrogen from the position next to that carbocation. In this case, there's no hydrogen at this position, and there's no hydrogen at this position, so we cannot do E1. So you would only get, so no E1, you would only get SN1, and so that means that the methanol will come in and do a substitution reaction, and you'll get, I'm going to cheat and do minus H plus all in one go, and you would get your substitution product as your only possible product in this case. Right, so you do have to watch out. Sometimes you won't be able to do elimination if your substrate is set up in such a way that there are no hydrogens at those neighboring positions. This is one of those things that is always important to watch out for, right? You have that second step of removing the hydrogen from the neighboring position. The hydrogen has to be at the neighboring position and there has to be one there for you to remove. Okay. These are E1 reactions. They're very straightforward compared, they're very much just an SN1 reaction, except for instead of having a nucleophile come in, you're just doing a Bronsted-Lowry acid-base reaction at a neighboring position. You're going to make the same carbocations, the same rules apply, all that other good stuff. Okay. The next video will be E2 mechanisms, which of course are like SN2 mechanisms, except for the same difference. We're going to have a Bronsted-Lowry acid-base reaction going on. So stick around for that one.